I want to talk a bit about ratio, rate, and proportion. They're three different things, but they're very closely related. They have a lot of things in common. It's super handy math that most people end up using all the time, but don't even realize they're doing it. We'll start with ratios, hopefully. So a ratio is a way, like these all are, of showing the relationship between two quantities. But the deal is with a ratio, if you want to be a ratio, both quantities must have the same units. So, if you're talking about a score, 5 points to 10 points, that's pretty straightforward. If you're talking about a test or 13 marks out of 20 marks, that's comparing your score to the total marks available. But what if you talk about one teacher in a class with 32 students? How are those the same thing? Well, you can stretch it a bit. We're all people. 1 to 32 is the ratio of teachers to students when we're all people. When we write a ratio, we have a few ways of doing it. The most useful one, I think, is to do it as a fraction, where you're comparing 13 out of 20, right? The first quantity is your numerator and the second quantity is your denominator. But what you often see is with a colon, and that's fine. You can work with that too. It's just sideways instead of up and down. So the scale of a blueprint, you'll also often see something like 1 to 50. And you can also use words. 1 to 50. 13 out of 20. One teacher for every 32 students. Or other kind of mixes that you make in a certain ratio. When we're communicating ratios, it's really important that you respect the order that you hear things in. If I say the ratio of dogs to cats, dogs are always going to be the first quantity, the numerator in a fraction, or once again, if you're using a colon, the first quantity. So the 3 represents the dogs. If I said cats to dogs, the 2 represents that. And I said cats to dogs, suddenly your ratio would either be 2/3 or 2-3, because we're talking cats to dogs. If we were saying dogs to total animals, 3 to what? We've got, well, let's say this is all the animals that are in there. I wasn't very 3 to 2. So we've got 3 dogs, 2 cats. The ratio of dogs to total animals is 3 to 5. Cats to total animals is 2 to 5. Total animals to cats is 5 to 2. You get it. We generally speaking, we want to reduce our ratios to lowest terms like we do with fractions by dividing by something that goes into both quantities. We want to keep these with whole numbers too. I say usually because there's other instances where we kind of prefer a unit ratio, like I'm thinking of in engine compression when you say 14.7 to 1. You're keeping a decimal, but that's in order to get that 2-1 ratio going. So grain of salt for that one. So if we were practicing reducing this and I see 14 to 10, 14 and 10 are both divisible by 2. So that could be 7 to 5. And that's as far as you can go there. Nothing goes into both 7 and 5. By the same thing, we can maybe reduce number 2 by dividing both sides by 10 to start. Maybe we're even super smart and recognize that 3 goes into both 15 and 24, and we can reduce that to 5 to 8. Now, nothing else is going to make that smaller, so this ratio, an equivalent ratio in lowest terms would be 5 to 8. 70 to 90, all I'm going to get to do is 7 to 9. If you have a decimal like this, I always recommend the first step is to get rid of the decimal. So if I have 0.25, if I want to change that into a whole number, I don't want to make it 2.5. The easiest thing to make it is 25. I do that by moving either the decimal over twice, if you think of it that way, or multiplying by 100, and it becomes 25. If I multiply 0.25 by 100, I'm going to just do the same to the number 1. So I start at 25 to 100, and then I reduce if I can. 25 happens to go into 100, so right away I can make this 1 to 4. Circling back, we said that ratios had to have the same unit. So if I'm talking about 3 months to 3 years, months and years are not the same. They measure time, but they are different measures of time. So we need to make them the same unit in order to compare them with a ratio. So best practice, put it in the smaller unit. So if I was going to make months into years, I'm going to start with a decimal right away. So go the other way. So keep the smaller unit, 3 months to 3 years. And if there's 12 months in a year, 12 times 3, 36, which we can reduce to 1 to 12. So that's like 1 month out of every year, but we expressed it differently. $5 to 60 cents. We start by measuring things in cents. 500 to 60. Divide both by 10, 50 to 6. Divide both by 2, 25 to 3. 62 meters to 2.48 kilometers. So we have to know metric a bit. That's coming. Meters, 2.48 kilometers. There's 1,000 meters in a kilometer. So we multiply 2.48 times 1,000. And we're going to get 2480. These are both even. So we're going to divide them both, by 2. And we get 31 to 1240. Now 31 is a real ugly number, but check. See if it goes into 1240 evenly. If I put it in this question, it probably does. It does. We can reduce this by dividing both sides of our ratio by the number 31 and get 1 to 40. Ooh, nickels and dimes. 5 and 10. They're not going to be the same, but they are both a type of cents. So we know that a nickel is 5 cents. So 3 nickels has a value of 15 cents. We also know that 2 dimes are 10 cents. So 2 dimes have a value of 20 cents. So we're starting with 15 to 20. Both those numbers are divisible by 5, and we drop it down to 3 to 4. The last one requires you to know how many days are in a month. There are 4 days in this month, which has 30 days. So we start with 4 to 30. We reduce it to 2 to 15, and we're done. The next thing I want to talk about is rates. So a rate kind of looks like a ratio in a way, sometimes, but they're comparing different units. So you're going to see the units because otherwise you don't know what they are. Like the ratios, the units kind of came in the sentence that went with it, and you just had 2 numbers. You didn't put the units in with it. So if we look at this, 55 miles per hour, that's 55, and notice that word per is always there for most of them. In, per, for are keywords. 55 miles per hour, so that's 55, and we're comparing miles per hour, which is really like we're saying 55 miles to 1 hour, right? But because we have the number 1, it's what we call a unit rate, we can kind of drop it and just say per hour. Same thing here. $3 for 1 kilogram, or simply $3 per kilogram, like you see at the grocery store. This one's a little different because it's $1.95 for 3. So it's 1.95 to $3 to oranges. But if you wanted to find how much a single orange costs, what could you do? You would take 1.95, the cost of 3 oranges, divided by that 3 to find out the cost of 1 orange. So each orange is 65 cents. So 65 cents per orange. Both are rates, but the second one I did is a unit rate because it's per one thing. And unit rates are always the same. You're saying how much for 1. So if I want to know what the price of gas is, in this example, we're doing for 1 liter, right? So we're just trying to divide and figure it out. If I pay this many dollars and I got this many liters, old school, the price per liter was 2020 prices, $1.22. So just a couple of examples. If 500 bolts cost $18.65, what is the price per bolt? So when I see price per bolt, that means I want to express this as dollars kind of divided by bolts. So instead of doing 500 divided by 18.65, which is tempting, you're going to do the dollars, 18.65, divided by 500. It's going to be a very small amount. That's fine. And you're going to get 0.037 per bolt, rounded. So that's 3.7 cents a bolt is what it is. Second question, tricky. if I usually drive 104 kilometers per hour, this is a unit rate they've given me already. So I know it's 104 per 1. So I need to find what that is equivalent to in 136 minutes. So first things first, you can have kilometers and hours, but you can't have kilometers, hours, and minutes. So we're going to take that 136 minutes. We divide it by 60 because there are 60 minutes in an hour. That's kind of like a rate, isn't it? And we get 2.267 hours. Okay, so if we drove 104 kilometers in 1 hour, and we're going to look at how to set this up in the proportion section, but right now I'm just going to say, well, here we go. We're going to drive 235.7 kilometers. Price comparison. Okay, so we're going to have situation A, the 3 bottles, versus situation B, which is the pitcher. So you can work this out a couple of ways, and we're going to make things. So first thing, I'm going to go, how much does it cost for a milliliter? So I know that the lower price will be better. So we have to be careful. We have 3 times 341 milliliters of the beverage in situation A. So we have to do that math first, and that gives us 1023 milliliters. 3 times 341. Okay. And I'm asking how much it costs per milliliter. I think that's what I said. Yeah. So we're going to take, for situation A, we're going to take 1650 and divide it by, I'll just use the fraction bar for that, 1023, and that gave me about 0.01613, very tight, dollars per milliliter. So that's the price per milliliter in situation A. Situation B, we take the $20 and we divide it by 1200 milliliters, and we're going to get 0.01667 dollars per milliliter. So obviously, from this, I would say situation A is the better one. But what if instead you had been like, oh, I did how many milliliters you can get for $1? That is still a unit rate. That's fine, and it's perfect for comparing. In that case, the math is just flipped. 1023 divided by 1650 compared to 1200 divided by 20. And if you do this one, you're going to get 62 milliliters per dollar. And if you do the second one, situation B, you get 60 milliliters per dollar. So notice, when I did dollars per milliliter, I was looking for the lower number. How much does it cost per milliliter? I want it to be lower. But when I do milliliters per dollar, I'm looking for the higher number. Situation A is still better because I'm getting 2 more milliliters for every dollar I spend. When we work with proportions, we're using ratios or rates, whatever, we can use either. But what we're doing is we're saying they're equivalent and we're solving a proportion, or we're trying to find out if they are equivalent. So if we have 9 over 12, or 9 to 12 is proportional to 3 to 4, that's the same way as saying, 3/4 is equivalent to the fraction 9 over 12. And, there's other fancy ways to say, like 3 is to 9 as 4 is to 12. Notice how you're keeping your numerator, your first number, straight, and your denominators, your second number, straight. Sometimes you'll get questions that are like, are these proportional? Is this the same amount? Is what they're really kind of asking. So if you had 21 to 49, is that proportional to 24 to 56? It's really hard to think of that in your head. But if you just do fraction math, set it up as 21 over 49 and do that division to find out what the decimal value of 21 over 49 is, then go ahead and do it again on the other side, 24 divided by 56. And if you get the same number, that means that your two things are proportional. And solving proportion happens all the time when you are making a recipe and you want to double it or triple it. You're using proportions, right? Or you're like, I only have this many eggs and the recipe calls for this. You're going to solve everything using proportions. And very classically, if you are doing a gas oil mix for a 2-stroke engine, you're going to use proportions to figure out how much oil to add in any situation. So set up here. Here's the question. My chainsaw takes a 40-to-1 gas to oil mix, 40 parts gas for every part oil. I was given 15 liters of gas in a can, or I acquired 15 liters of gas in a can. How much oil do I add to make it a 41-to-1 mix? So here we go. So we've set up this thing, and what we have done is these go together. We know this, but it's parts gas to 1 part oil. And what I'm solving is parts gas, 15 gas, to how much oil? How much oil do I need if I only have 15 gallons of gas, or sorry, liters of gas? Okay, so here's where we were on the last slide. And we're going to use cross multiplication, which if you know it, you go ahead, do your cross multiplication. When I say magic banana, it's a shortcut. So for a magic banana, you set it up, you put everything in the right place, gas on top, oil on bottom, 40-to-1, 15 to what? And the rule is you're looking at the diagonal. So the diagonal that has 2 numbers in it, like no question mark, no X, no unknown, is going to be multiplied. So I'm going to multiply 1 times 15. It seems kind of dumb in this one, but bear with me. And the leftover amount, the loser, is the divider. So if you want to solve for the question mark, that's all you have to do. Find the diagonal numbers, and it doesn't have to always be here. This question mark could be in any of these 4 positions, and this will work every time. So we do 15 times 1 divided by 40, and that will give you the missing quantity, which I believe in this case would be 0.375 liters of oil. How can I test if I'm right? Divide 40 by 1. Well, that's 40. Divide 15 by 0.375. It should also equal 40. So a couple of practice questions. We have a bus and it travels 675 kilometers in 18 hours. So as I read this information, I'm like, okay, you're telling me information about this bus traveling. So I'm going to write it down. And I have a van that's traveling 820 kilometers in 20 hours, okay? Do they travel at the same speed? I don't even care which one's going faster. I just want to know if their speeds are the same. Well, obviously, to find the bus speed, you're just going to divide 675 by 18, which gives you about 37.5 kilometers per hour, right? And when you divide 820 by 20, you get 41 kilometers per hour. 37.5 is not the same as 41, so they did not travel at the same speed. This is a neat Canadian one. I can drive 70 kilometers on 5 liters of gas. What is my fuel efficiency? Here in Canada, we like to do our fuel efficiency in liters per 100 kilometers. So instead of writing the first known kind of side of the equation, I'm going to start with my unknown side. I want to know how many liters per 100 kilometers. And that will give me the whole thing together will be the fuel efficiency. So I just have to match up my quantities in the right place. So the liters went on top. So I'm going to put 5 liters on top on this side and 70 kilometers on the bottom. Okay, so we're ready to magic banana. We take the 2 numbers, so 5 times 100 divided by the leftover 70 will give our answer. So question mark is going to equal 5 times 100 divided by 70, which is 7.14 liters per 100 kilometers. We have paint coverage, 2 liters for every 11 meters squared. I've been told I need to paint a certain area, so that goes with the area measurement. My question mark is the amount of paint I need. And then we have a bonus we're going to have to multiply to get $1 about. Once again, magic banana. The unknown amount is going to be 2 times 875 divided by 11, which is 151.1 liters. And then if I want to know how much that costs, all I do, if 1 liter costs $12.50, you could set up another thing. You could, oh my God, I'm going to make you do it. So we take 151 liters and we don't know how much that costs. How many dollars? We can set up a ratio with 1 liter costs $12.50. This is a long way to do it because you just could have done the multiplication right away, but it will still work. The 2 numbers are here. Our math is 159.1 times 1250 divided by 1, which is going to make no difference. And we're going to get 1988.64. So not necessary to use the ratio in that one, but it works. Number 4 is a really neat one, mixing by parts. So whether your recipe is for cupcakes or concrete, this works if it's a part recipe. So I see that I have 66 kilograms of concrete, which is my final product. And I made it out of cement, and gravel. And the ratio for making them is 1 to 2 to 3. So that means cement to sand to gravel. Cement to sand to gravel. Because that's the order I read it in. Okay, so remember that order matters. All right, well, let's think about the parts. If we have 1 to 2 to 3, how many parts do we need in total? 1 plus 2 plus 3 equals 6 parts. If I'm going to make 6 parts of this concrete and it's going to be 66 kilograms, what did I do to turn 6 into 66? I multiplied it by 11, right? So that's like a little scale factor there. If I want to find out how much cement, sand, and gravel I need, I just take each of the quantities or the ratios, parts, and multiply by 11. So I'll need 11 kilograms of cement, 22 kilograms of sand, and 33 kilograms of gravel. And you'll notice that if you do 11 plus 22 plus 33, it adds up to 66. We talked about scale factors in class, but I think you're going to hit that in a drafting course. So I'm going to walk away from it and move on to inverse proportions. So everything we've looked at until this point has been directly proportional. That means if one quantity goes up, so does the other, right? If you drive a further distance, and let's say the speed's the same, it takes more time. If you buy more bananas, it costs more money, and so on and so forth, right? We can also have what we call inverse proportions, which means that if one quantity goes up, the other quantity goes down. And we can think of this like efficiency, right? If you add more workers to a job, it should take less time. If you drive faster with the same distance, your trip should take less time. So thinking about those efficiency situations. So now when you go through your word problems, you kind of got to be like, okay, is this direct proportional or is it indirectly proportional? If you find that you have something to be inverse or indirect, I'm just going to quickly go here because I talked about it without going through this slide. This is what you're doing. 1 up, 1 down, 1 down, 1 up. That means it's inverse or indirect. So we need another method, or we need to bring that into our calculations. So you would set things up the way you normally did. And I'm going to just write on the side here. So if you have 5 workers and it took 7 days for them to do a job. And now what have you changed? You're going to take 11 workers. And you want to know how many days they'll take. So if you solve this right now, it'll be solved as a direct proportion. And you'll tell me that it takes 11 workers more time to do the job than it took 5 workers. And that doesn't make sense. So the minute you've established you have an inverse proportion, set up your ratio, and then do this crazy move. Swap the numerators. So we're going to change it to 11 over 7 equals 5 over question mark. These two have switched places. Then solve it like you always do. The unknown is equal to 7 times 5 divided by 11, which should give you about 3.18 days. This is the slide we ended our class with. There's some assumptions here that make no sense. If you're driving around town with 32 liters, that's not going to be the same fuel efficiency as driving on the highway from Ottawa to Toronto. But some assumptions are made. So what I'm going to do is just make sure that we have the answers written down, which you can have from Brightspace too, but just in case you're not accessing Brightspace with my class and learning it. And then I'd like to see you get your answers on your own. You know where to find me if you need help. Ooh, not kilograms. Should not be kilograms. It should be kilometers. This one, rounding to the nearest tile, should give you 87 tiles. This one's tricky, and the trick is in where you put things. Which one's a shadow and which one's a height? You should get 12 meters. Ooh, this one, think about the type of proportion this is, you should get 108 kilometers per hour. This one takes in a bit of like knowing how many minutes happen in a day, but you should end up at 7,200 milliliters. That's a good leak. Once again, watch out for efficiency questions. Note why this will take 1 hour and not what you thought it might have. And here, careful that you line up your Canadian dollars both in the numerator or both in the denominator, and your American dollars both in the numerator and both in the denominator. So hopefully you get the same answers. If not, get in touch and I'm happy to go over any of them with you.